It's my great honor and pleasure to introduce our distinguished lecture series speakers, Lenore and Manuel Blum. Lenore has a history with TTIC. She was here for the first 2 years, working with Steve Smale as part of a long-term project on real complexity theory. What's the theory of computation when your numbers are actual real numbers, not just floating points? She's also worked for womeninSTEM, and she's had various leadership roles, such as being vice president of the American Mathematical Society. So Manuel is a 1995 Turing Award winner for contributions to computational complexity theory, and that's contribution to cryptography and program testing. And Manuel, I feel a certain kinship with him because I think through his whole life he's been very interested in some of the deepest, most fundamental questions of mind and AI, and he actually worked under Marvin Minsky, who's someone I knew as a graduate student. So I'm very pleased to have them both here today to talk about consciousness.
Thank you, David. Okay, so this is possibly something totally different. We look at computer science perspective on consciousness, and it's really joint, it's a family affair, as you notice. Me, Manuel, and with help from Avram, actually. So I'm going to give sort of an overview, and then Manuel will go into a few more details. I haven't seen his talk, so I'm not exactly sure what he's going to do, but okay. And it is work in progress, and it's at a very high level that I'll be talking, and a lot of the things need a lot of the details to be worked out. We're working on a monograph right now, putting in a lot of details, but we can use a lot of help. So this looks like a great audience for help with the ideas that we have. Okay, so say a few words about consciousness. Throughout the millennia, consciousness has been the purview of philosophers and theologians. Until about 35 years ago, the scientific study of consciousness has been taboo, and now it's actively pursued by cognitive scientists, neuroscientists, psychologists, AI researchers, physicists, mathematicians. So taboo, and now it's actively pursued. So what changed? Okay, first of all, in 1990, there was the invention of fMRI technologies, which allowed neuroscientists to look non-invasively in the brain, to some extent, to see what was going on when people were doing different activities. So at least there was a way to non-invasively. So prior to 1990, most of the information came from pathological work, people who had pathologies looking into the brain. And then in 1995, Francis Crick, who's a Nobel Prize winner, wrote this book about the astonishing hypothesis, talking about that now is a good time to study what neuroscientists to study, maybe neural correlates of consciousness. And that gave a sort of authenticity to people to start to look, to scientists at least, that it's okay to look at consciousness. And 1991, actually a little before that, Daniel Dennett, philosopher who actually tragically, just died last week, talked about a functional perspective on consciousness, which is very relevant to our approach as well. And in 94, 95, philosopher David Chalmers talked about the heart problem. And what he did there was he actually put together, he focused on two areas of consciousness. One which he called the easy problem. And the easy problem of consciousness are those that seem directly susceptible to the standard method of cognitive science, whereby a phenomenon is explained in terms of computational or neural mechanisms, and this is often called functional, access consciousness, cognitive consciousness, okay, kind of more computational. And then he said the hard problem, the really hard problem of consciousness is the problem of experience. When we think and perceive, there's aware of information processing, but there's also a subjective aspect, and that's often called phenomenal consciousness. And many people took the easy versus the hard problem as really a gap in two kinds of consciousness. Like that really is stating that there are really definitely two kinds of consciousness. and never the twain will meet. But we're taking the hard problem as a challenge to actually show the hard problem can be viewed computationally. So we see that as a challenge, and I even believe David Chalmers actually sees it that way today. So the hard problem is usually associated with qualia, the feeling of what it is like, the feeling of what it's like to be a bat. That was famously an article by Thomas Nagel in '74. And many focus on what it feels like when you see red. And not just the color red, but maybe if you're in China, what red might mean to you versus if you're someplace else in the world. It may have different meanings. So what it feels like when you see red. Okay. For us, the easy problem is to make a robot that simulates feelings, for example, pain and joy, and the hard problem would be to make a robot that truly experiences feelings, for example, of pain and joy. And here you see Sophia simulating many emotions, and there she is, she's ending up with pleasure and joy. And although Sophia's expressions may simulate pleasure, she has what we might call acute anhedonia. Many philosophers would say she's a zombie. And anhedonia is, if you get knocked on your head in a certain way, you would start to have this disease called anhedonia, which is the inability to experience pleasure. There's another thing called pain asymphonia, which has to do without experiencing pain. Also, Manuel may talk about that. Okay. So I'm going to talk about what we call the Conscious Turing Machine, which is our theoretical computer science framework for looking at a conscious, and we even think of conscious AGI. And our goal is to have a very simple model that's formal, gives us some insights and also predictions. Okay, now my talk will be, I'll talk about the CTM, give a brief introduction, I'll say what it is not, and then I'll give it structure and dynamics, and then I'd like to talk about two kinds of consciousness, one we call conscious attention, and that's analogous to cognitive access or functional consciousness, and then feelings of consciousness, more subjective. So the first deals with, we believe, the easy problem, the second, the hard problem. And then I'd like to look at the alignment of the CTM with other models of consciousness. Okay. So the Conscious Turing Machine is inspired by Alan Turing's simple yet powerful model of computation. So that's an inspiration for us. It's very simple but powerful, we like. And Brené Brown's global workspace theory of consciousness. It's called the theater model. And the way Bars describes consciousness, he does it through a theater analogy. And he says, consciousness is like the activity of actors in a play performing on a stage of working or short-term memory. The inner speech actors off on stage, so I'm like the consciousness on the stage here in this room. And their performance, my performance, is under observation by a huge audience of powerful, unconscious processors in long-term memory that are sitting in the dark, or here in the light. And the unconscious processors, then you guys vie amongst yourselves to get your script, query, your information to the stage to be then broadcast to the audience. And that's what we process. And I like to explain this with this kind of example. You're at a party and you see somebody you know, but for the life of you, you can't remember their name. Familiar or not? Okay. So what's going on? So what happens is, then you get home and the name sort of pops up, but what's going on when it's too late, actually? So some processor is very embarrassed because here's a person that you know very well and you can't remember her name. So it's saying, what's her name, with a lot of weight to it, and it gets up into the stage of short-term memory, right? And then that gets broadcast, and you recall where you first met, maybe in TTIC. Gets up to short-term memory, gets broadcast down. Something about what she does, of course, she's studying machine learning. Gets up to the stage, gets broadcast down to all the processes. Now all the processes have a lot of information. Another one says her name starts with T, gets broadcast. And finally, when you get home, a half hour later, her name Sarah comes up to the stage. The conscious short-term memory from the audience of unconscious processors with the thinking, searching. Now, of course, there's a disconnect here between the T and Sarah, and I'll get to that later, okay? And the conscious self on stage doesn't know how or where her name was found, Okay, so the conscious self is not privy to the workings of the unconscious self. There's another effect that's kind of similar, a little different, which I like to call the Poincaré effect. And Henri Poincaré was a mathematician last century. And he talks about really working day and night on a very hard problem, which he couldn't crack. He was really desperate. And luckily, a friend calls him up and says, how about let's go on a hike? And he says, great, well, he likes hiking. And then he gets on the bus to get to the place for the hike. And he says, as I'm about to board the bus, the idea came to me without anything in my former thoughts seeming to have paved the way for it. And what happened is he saw that two ideas that he knew very well, but he had never seen the connection before, he saw that they were kind of isomorphic ideas. And what's happening is here is unconscious. He knew a lot, he'd been studying a lot, went into the unconscious long-term memory. And then when he relaxed a little bit, not thinking about it, those processes were working really hard. They're down there they're linked together and they're working hard. And then one of them pops up and says, hey, these are kind of connected. So that's a little different phenomenon, but in a similar vein. Okay, so now I'm going to go into the structure of the conscious Turing machine, but before I do, I'd like to say what it is not. It is not a model of the brain. Okay? It's this very simple formal machine model of consciousness. It considers the brain at a very high level of abstraction, at levels well above that of neurons and neuronal activity. Okay? It's not a brain. The CTM is not even a standard Turing machine. It's not even a Turing machine. What gives the CTM the feeling of consciousness is not the input-output map, nor its computing power, but what's under the hood and its dynamics. So I would like to tell you soon what's under the hood. And it's not even a global workspace model, standard one. It has important differences. So for example, VAR says the audience members get together and decide for themselves which one gets up on stage. It does not have, we have a very well-defined competition for global workspace access to get up on stage, and I will talk a lot more about that. And our subjective feeling of the CTM results from interactions between its evolving models of the world and its global workspace. So Barr's model does not have models of the world, which we find is really critical for the hard problem, for the machine to have the feelings of consciousness. And our machine also has no central executive, and that turns out to be very important for making it a good model for AGI. It's kind of like a federation. Okay, so here's the structure. Let me just say it's a 6-tuple. The CTM, yes?
I might have missed this, but do you distinguish between subconscious and unconscious?
Conscious and unconscious? Well,
Subconscious and unconscious?
Subconscious and unconscious? Yeah. I'm going to really just talk about unconscious and conscious, and we can talk about subtleties later, yeah. But that's okay. So, right. I guess other questions will maybe lead us to the end. Okay. Okay. So the CTM is a 7-tuple. STM, LTM, uptree, downtree, links, input, output, and I have to define these formally. The time is measured in discrete clock ticks, T01, and it has a finite lifetime, like 10 to the 11th. CTM is born at time 0, and it has a finite lifetime, T. STM is a small memory capable of holding a single chunk, and I'll soon define chunk. LTM is a massive parallel collection of n parallel processors, and we're thinking of this as more than 10 million. 10 million cortical columns in the brain, and where each of those have millions of neurons. So we're thinking of something more than 10 million processors. The uptree is an up-directed binary tree of height h with n leaves, 1 leaf at each long-term memory processor, and a single root in STM. That will be the conduit for the competition. The down tree is a simple down-directed tree of height 1 with a single root in STM and n edges directed from that root to the leaves, 1 leaf in each LTM processor. That's for broadcast. Links are channels for transmitting information between processors. Inputs come from the outside world into LTM via sensors. Output goes from long-term memory processors to the outside world via actuators, and RM is the outside world. Okay, I don't expect you to remember all this, but just to know that there's a formal thing. Each of these things have a formal definition, and what I'm going to do is show it to you by a cartoon. Okay, so we'll go through each of these by cartoon. So we start with tiny short-term memory. That's our STM. Okay, that's our stage. And our stage can hold one chunk of information. Now, the chunk in our case will be a gist of information plus a weight that's given to that. It can be a positive or negative weight, how important that chunk is. Now, it's not the 7 plus or minus 2 chunks that Miller talked about in the 50s. In fact, one of the reasons that the US phone numbers, I think, are 9 digits or 7 or 8 digits is because Miller said that's all you could hold in your short-term memory until you got someone gives you their telephone number. You need to get a piece of paper to write it down. You couldn't keep more than 7 plus or minus 2 digits in your head. So a chunk is either a digit, a little gist of information with some short query or something like that. Okay. But we'll formally say what we say a chunk is. Then we have a large collection of, that's LTM, long-term memory processors. They're independent at first, they're very powerful, and they will be connected over time. But originally in our baby CTM, when it's born, there's no links there. So that's LTM. Okay, and that's our audience. Then we have inputs coming from the external world through sensors like eyes, ears, nose, touch. So information then going out from particular long-term memory processors through actuators like legs, arms, voice, whatever, to affect the outside world. Okay, and at each moment in time, every processor puts a chunk of information into a competition to get into short-term memory. And so now let me just formally define chunk. So a trunk is a 4-tuple plus auxiliary information. It starts off with the address of the processor. We have 10 to the 7 processors, that's just a 7-digit number. So we want to make sure this chunk is very small. T is the time the chunk is put in by the processor. Weight just is the information in brainish that the processor wants to get onto short-term memory. Now, brainish is our internal language. Every processor has its own language, but brainish is a multimodal language. So it's a language that all of the processors will learn about, and each word is a fused, like it could be a word, a smell, a taste, a sound, whatever. So that's our internal language. Weight is the valence importance or the confidence that the processor gives its gist. So like what's her name would be the gist. That was the one. What's her name would be the gist, and that processor would have put a very, very high weight to what's her name in that example we had. And then chunks compete locally. The local winner moves up one node of the tree. And it's sort of like a tennis tournament, but fairer. Your chance of winning doesn't depend on your location in the tournament, but only on how you compare with the other 10 million competitors. And then we'll go into the details here. But it's really important that it doesn't depend where the processor is located, because we don't want to be moving these processes around. And we don't want to move around in our head, and then we don't want to move around in the machine. So that's very important with our competition. It's independent of location of the processor. Okay, so there's an uptree competition. A chunk gets into short-term memory that wins the competition, and we call that the conscious content. So the chunk that gets into short-term memory is the conscious content, and it's immediately broadcast down the downtree, immediately to all the processors. And at that point, we say, conscious attention in the CTM is the reception by all long-term memory processes of the broadcast of CTM's conscious content. So the winner is the conscious content, and then it gets broadcast down immediately, and we call that's when the CTM is paying conscious attention. Okay, this is attention. Okay. Okay. And it's a little bit like there's a neuroscientist or psychologist, Libet, who pointed out quite a while ago that there's a delay between you're making a decision and you're being conscious of it. And you can sort of see that here in the CTM also. The processors are putting in chunks into the competition. It takes a little while, not too long, but it takes a little while to get into the short-term memory, and then immediately gets broadcast. So if we have the timing right, maybe it's like 250 milliseconds to get into the onto the stage and then immediately broadcast. So there's a little bit of consistency here with what we know psychologically. So as I said, to start with, these processors are independent. But as time goes on, links form. So for example, the processor that asked, what's her name, will want to link up with the processor said that her name was Sarah, the right name, because that processor seems to have the right kind of information that the other processor wants. So as processors see that other processors have information that they would like to use or they have kindred ideas, they start to form these links. And so it's like a Hebbian type principle that processors have common interests linked together. And again, they link and they communicate via brainage, which is a rich multimodal inner language. So it merges words, images, sounds, sensations, smells into one particular word. And Paul Yang, who just defended his thesis successfully last week at Carnegie Mellon, is working on a formal computer multimodal language, which he's calling brainage as well. What links do is they turn conscious communication into unconscious communication. So, for example, when you're learning to ride a bike, everything is done very consciously. Okay, you have to check out your movements, but after you get enough practice, it all becomes the links form between the different, between the different parts of your different processors, and a lot of things are done unconsciously, except if you're riding down the street and a car comes to you, then you flip back into consciousness. But most of that's unconscious. On the other hand, the Poincaré effect can be explained also in terms of links. So after a lot of links have formed, a lot of the processing is done unconsciously in Poincaré until one processor decides, hey, I have a lot of new information, I'm going to put a lot of weight on it, we'll get into short-term memory. So that's also unconscious communication turning into conscious communication. Alison Gopnik has always said that, I don't know if you know Alison, she's a child, she looks at consciousness in babies and infants and learning and cognition, and she always says that babies are more conscious than adults. And I thought that was very strange, sorry, just seemed very strange to me. But in terms of the CTM, in terms of conscious attention, it makes sense because the baby doesn't have many links formed between its processors. So everything it's doing is going through short-term memory, through consciousness. It's, a lot of different things, and maybe it's not making sense of all of them at once, but a lot of it's going that way. So in terms of conscious attention, going through short-term memory, I think Alison is correct. But attention is not all you need. Okay? That's the second part of the talk, which I'll get to in a bit. Okay, so attention is more closely related to the easy problem, but you need more. Okay, and this is where long-term memory processors come in. And there are special long-term memory processors, the inner speech processor, but particularly the model of the world processor. And hold that in your head because I'm going to give some of the consequences of attention, and then I'll go into the model of the world, which is critical for the more phenomenal feelings of consciousness. Okay, in their formal model, at time equals 0. All of long-term memory processes are generic with certain basic built-in properties, some learning algorithms, tendency to go to the positive, and their functionality will emerge over time. But for now, we designate some important long-term memory processors built in, like the modeled world, but also we allow off the shelf. Why not? ChatGPT, why not? We're all using it. Why not let our machine use it as well? And they also, processes may also have functions analogous to brain processes like the visual cortex, the hippocampus, thalamus, and so forth. Okay, more about the long-term memory processors. Okay, so remember that what's her name example, okay? And one of the processors said her name started with T, but it really, her name was Sarah. Well, these processors need to have something built in, which is a modification of the sleeping expert algorithm, which will say to that processor that said her name started with T, hey, you were too bold, you gave too much weight to your chunk. Her name started with T. Hey, cool it a little bit, next time don't give so much weight. And then there was another processor who said her name started with S, but that processor was so timid, didn't give enough weight to it. And so its sleeping expert algorithm will boost its weight next time around. Say, hey, be a little bit more sure of yourself, give a higher weight, okay? And that's what the Avram's algorithm will, or modification of his algorithm, and he can tell you about it sometime, is the one that does the balancing here to help correct the weights here. I'm not going to go into the details of that. So already you can see something we call predictive dynamics working in this very simple model. It's cycles of prediction, feedback, and learning. So when processes put a chunk into the competition, you could say that's a kind of prediction. Prediction, her name starts with T, okay? Or when it sends a message to the external world and does something, that's a kind of a prediction. And then it gets feedback, let's say, from the broadcast, what the right answer was, for example. There's feedback coming in all along, and then there's, from the feedback, there's learning, okay? And so there's a kind of cycle, which we call predictive dynamics. Just seeing here, there's a lot more going on internally in the different processors, but you can globally see some of this dynamics already. So the reasonableness of our model and definitions lie in the number of concepts that the model explains easily. And actually, I'm going to give you 3 examples. They're standard examples that are given in any psychology class. But we will explain them very simply here from the CTM, and I think that's kind of fun. So I'm going to look at, and our explanations actually agree at a high level with the neuroscience and psychology explanations. So here, the first example I'm going to talk about is called blindsight. And here's a guy sitting in a cluttered room, right? And he's asked to go to the other room, but he says, I can't see. He says he's blind. And nevertheless, he gets up, walks to the door, avoiding all the obstacles, okay? This is called blindsight. And what's going on? Okay, so let's give an explanation from the CTM. So we're going to assume for this case that this CTM or this guy already was sighted for part of his life, and then he became blindsided at some point for some reason. Okay, so in other words, links had a chance to form, for example, from the vision processor to the motor processor, links had already formed. So when the information comes into the vision processor or some of the other processors from the outside world, looking around the room, information then is transmitted through the links, and so that his vision processor seems to work properly, and it sends messages via the link to the motor processor, which sends messages to the walk actuator, and the guy walks around. But the connection from vision to short-term memory doesn't exist, or it's broken, or there's something going on that he's not putting enough weights to it, that processor's not. And so because the information doesn't come up to short-term memory and isn't broadcast, he doesn't have a conscious sense that he can see. It's just not going through short-term memory, it's not broadcast to all the processors. And this is, again, without the vision processor having access to SDN, the CTM has no conscious sense that he can see. The connection to SDN is damaged, but partial processor links are functioning. So that's our explanation. And it does, at a high level, correspond to information in the literature. We're also predicting from this that blind sight requires prior sight. And I know a number of people who've worked on blind sight, and I've asked them, have you ever met somebody who has blind sight who wasn't sighted before? And they say, no. Maybe possible, but no, they don't have it. So we're sort of suggesting it requires prior sight. There's another example that you may have seen called inattentional blindness. This is a little video sent, shown to people, and they asked, count the number of white-shirted players that are passing balls. They're all passing balls, okay? And they all mostly get it correct, 15. But then they're asked, why didn't we or the CTM see the gorilla, which is in plain sight? So if you haven't, you've probably seen this before. If you haven't, there's a gorilla up there in plain sight. And again, the CTM explanation is when the CTM is given a task, its processors give higher weight to the task, in this case white, and it won't be conscious of other things that are given lower weights. Okay, so the weights that only get into the things that go into short-term memory are those that are looking for white shirted, something white. Everything else doesn't get in, maybe in a little bit, but not too much. Okay. So, and this is the power effect of the weights given to GIS. So this inattentional blind, what you're not noticing, like the gorilla, is because your processors were told to look for white, so you're not giving a lot of weight to black stuff to look for. And again, this is consistent with some of the literature. And this is one of my favorite ones. It's called change blindness. And this is a little film. Again, here's a detective coming into a room. He sees a dead guy on the floor, little mansion there, right? He sees the people around him. Immediately, he's very clever, and he starts asking everybody, clearly somebody in this room murdered Lord Smythe. Each of you tell me your whereabouts. And then he goes to each of the participants and says, the maid says, I was polishing the brass in the master bedroom. And the butler says, I was buttering his lordship's scones. And later Smythe says, I was planting my petunias in the potting shed. And of course, the detective's very clever, and he says, Constable, arrest Lady Smythe from that information. And she says, well, but how did you know? And he says, Madam, and as any horticulturist will tell you, one does not plant petunias until May. Okay. But the bigger mystery is, why didn't we see the many changes here? You see the detective changed his coat from dark to light. The dead guy, if you notice, changed his clothes too, and his leg is off the floor. And there are a zillion, the flowers are changed. Every single item there has changed. You can see it, there are a zillion changes there. Now what's going on? Why didn't we see that completely? And here's our explanation from the CTM. Detecting change in the whodunit video would have required significant changes in the gist. Okay, the chunk has a gist of information describing the beginning and ending scenes. But in this case, size limitations on the conscious content and the clever scene transitions cause the high-level descriptions to be essentially the same. And so the same gist explains the first scene and the last scene. Right? The scene is the living room of mansion with butler, maid, and detective, and a man laid out on the floor. Right? Describes the first, describes the last. So you're not going to be able to put much more information in there when you're looking at this mystery, right? So it's the size of the gist, having that compact gist, and the size of resource limitations here that comes into account to explain this. And so it's the same gist, describes both scenes, and again, it does correspond with some high-level explanations. Okay, so I know I'm going over. I'm going to do 5 more minutes, Manuel, okay? And I'm going to part 2. Okay, so part 2 it's actually, why would a robot with a CTM brain feel it is conscious, okay? So this was the conscious awareness, right, more the phenomenological thing. Okay, the ability to create and utilize world models is key to CTM's feeling of consciousness. Okay, and the model of world processor is linked to and interacts with many processors. And here we have the world on the right and the model of the world on the left. And the model of world processor makes many models of the internal and external world. Okay, and the model of world processor maintains models of the world and of CTM in these worlds. The processor serves many purposes. It figures in explorations and planning. It's how the CTM understands itself and the place in the world. So it accomplishes its roles through its interaction with other processor, consciously or unconsciously, and making predictions and updating and giving feedback. And it tags elements in its various models of the world with multimodal brainage gifs, including labeling, actuators of self, when it consistently detects them carrying out requests. Okay, and here's a nice little example of a baby that's discovering its left leg, and it's understanding that by thinking about it, it can actually activate its left leg, and it's calling it so. It actually tries to look at its right leg and hasn't quite been able to identify that yet. So this is how the baby is starting to its baby's model of the world is starting to lay down. So when the model of the world processor detects the CTM thinking about its own consciousness, it tags CTM in its model of the world. It's conscious. And looking at the CTM from the viewpoint of the outside world, you see something about the CTM is conscious. Specifically, the CTM considers itself conscious. What is conscious cannot be the model of world processor or any other processor. Its processors have no feelings. They're just machines running algorithms. So we propose the view that CTM as a whole feels it is conscious is a consequence and part of the fact that the model of the world processor views the CTM and its models of the world as conscious, and that this view is broadcast to all processors and thus to all processors associated with feelings of consciousness. So, for example, when the model of the world processor detects the CTM paying attention to the brainish labeled sketch of the rose, the brainish labeled sketch is really, that's the information. It tags CTM as consciously aware of the rose. In other words, we can say conscious awareness is attention, but attention of brainish labeled model of the world sketches. That model of the world is really what it only sees and feels about the world, and when it pays attention to one of those sketches, it gets up into short-term memory with all this information and brainish in it, and that's broadcast down. That is what we call conscious awareness. So it's a little bit more than attention. It has to do with the model of the world. And this is kindred spirit to neuroscientist Michael Graziano, the attention schema theory, and it's also kindred spirit to Dan Dennett's view of consciousness. I just heard a talk that he gave very recently. Consciousness is the brain's user interface for itself. So that's very similar to what we're saying. And one way to see this is to see the consequence of mislabeling. So Cotard syndrome is a syndrome when people think that they're dead. And in their model world, they've labeled themselves as dead. There's something called body integrity identity disorder, where people feel maybe their limb, even though they feel it and they can use it, it doesn't feel like it's part of them. And they go to doctors in the US, they say, why not cut it off? And no doctor here will do that. So they go to Mexico, they come back crippled and they're feeling really good. They finally got rid of that leg that didn't feel like them. Okay, it wasn't felt like self. The label in the brain is not self. Phantom limb syndrome is a kind of similar thing. You have an arm that's amputated, but you still feel it's itching. You feel pain in that arm. It's still labeled in your model of world as self. Okay? There's delusional disorders, paranoia. You think your best friend is a spy. It's in your brain, this paranoia. It's in your model of the world. Okay, so a lot of this can be understood through anomalies, disabilities and stuff, what the model of the world is actually doing and not doing. And there are many, many other syndromes that we could look at. Okay, so should I stop here? So I just want to quickly say that you may have been reading in the paper that there are 10 million theories of consciousness, okay? And they're all fighting with each other, saying this is right and that's wrong and whatever. And there are all sorts of debates and things like that. But I'm not going to go through details here. But our machine actually aligns with almost every single major, and if you're interested, I can go into detail later, almost every single major theory of consciousness, coming from philosophy, coming from neuroscience, coming from IIT, which is a kind of a mathematical measurement, coming from the base, come from just many different things, coming from evolution, theories of evolution. Our theory aligns with all of these theories. And so what that does is it gives us a conclusion. And this is a conclusion on the debates, that since most of the major theories of consciousness align with the simple machine model, the CTM, one of the conclusions is that they are compatible, they're complementary, they're all looking at consciousness like they're looking at the elephant from different parts. And they're all right, but there are different aspects, and they all fit into this one model. So they're compatible and complementary. And our final conclusion, my final conclusion at least here, is that since most of the major theories of consciousness align with a simple machine model, CTM, AI consciousness is inevitable. Okay, so that's my end.
You have any questions? Somebody here asked a question about unconscious and subconscious, and there's nothing in the model that there's nothing in the model that would suggest that there's any difference that I can tell. But maybe you'll be able to tell. Yes?
What's the point of set the lifetime T for the machine? Why you have a limited time?
Limited time?
Yeah,
Because we have two reasons. One is because we'd like to model something like our brain, which has finite lifetime, but also the number of processors in this model is roughly equal to the length of time of the life in ticks. And that's important for reasons that we go into. So you can't do with infinite lifetime. Yeah.
I thought it was kind of interesting that the sort of input goes into the long-term processors in our brains. Don't you think that it's more like sensory input that then like interacts with short and long-term memory?
Yeah, so what we do in our model, this is a big difference between ours and bars, is like the eye, your vision is going into your vision processor directly. It's not going into consciousness. Has to be processed before it can get into your conscious. So I don't know if that's what you're asking, but we're having inputs going directly to processors, not to your consciousness. And that's a big difference between our model and ours. It's a big difference. Yeah.
So you had talked about feelings and consciousness. My understanding was feelings comes with two aspects. One is the mental dialogue, which you explained through brainish. The other is like in humans, we also have a sense of sensations, like something we feel inside our body. Suppose I think about a recipe, I look at it and there's something goes, and then I go back home, I keep thinking about it, and the sensations in my body, like my tongue gets wet or my stomach gets grumpy.
You've actually learned that. The baby has learned, when it's hungry.
Yeah.
This is when it's very primitive, doesn't have a good world model at first. It's hungry, and that's an uncomfortable thing, and that's associated with maybe the first feelings of pain it has. And then when it gets its milk, it's associated with the first feelings of pleasure. And these build up as more and more things happen that are pleasurable that they can identify with it, extend that. So the baby is developing its world model, and you're developing it as well.
So my question is that without having a lot of external sensory data, can I still, I'm internalizing most of it. Can the model, the model that you just proposed, also do that, and go into that loop of craving and aversion?
Okay,
Yeah.
so I didn't go through the different theories there are, but one of the theories is embedded, embodied, extended. So yes, our theory is very important that you're embodied. One of the theories of consciousness has to do with embodied, and because we have the sensors, our machine is embodied, actually. So it actually depends on those sensors, the consciousness, in part. it's embedded in the world because we can our machine is getting input from the world and it can actuate and can activate on the world. So it has that embedded in the world. And it is an extended, and that's another notion of consciousness, that there are libraries out there, but now there's ChatGPT and everything else, so your consciousness is quite extended. So those are one of the theories which in my list, embedded, embodied, and extended. There are several of them, yes. But I think that's what you're talking about, that those are very essential parts of consciousness.
Because the very conscious people are also aware that these thoughts, like if you look at somebody who's extremely conscious or maybe a monk, they are very aware that these thoughts are themselves creating this craving
Why
aversion.
don't we stop that here? Maybe somebody else has questions, but.
I have a
Yeah.
You mentioned again that several models of consciousness they are sort of compatible with each other. Could we say that this is sort of a Turing thesis for consciousness?
Yeah, I don't know. We're saying we have a minimal model. We're not saying it's. Yeah, I'm not going to say it's a church. The church priest. Yeah, I don't want to say that. No. But we do have a kind of minimal model, which is starting to get recognized. Right. It's very.
Coming back to the last slide you displayed, can we use this model to create a test for consciousness of AGI?
A test for consciousness.
Yeah.
That's a very good question. So, our machine, our machine can dream. CTM can form dreams, and dreaming is very much like a wake, except that you're not getting feedback from the outside world. You're not acting out, so they can be a little more fantastical. Okay, so one thing is saying that dreams, if you see it, and I think they're looking at this in animals. If animals are dreaming, that's a measure of that they're conscious. They're not telling you they're conscious, but dreams could be a good measure of consciousness, testing for dreams. But yeah, that's a big question of how to test for consciousness.
One of the problems in trying to get a test for consciousness is that you can make a robot dream. You can make a robot pass the mirror test for self-awareness.
Yeah.
So whatever the test is, I think you're going to have to look inside to see how it does it. You can to see that it's not been built in.
That's very hard to do, is how to see that something's not built in already. But my own view is that these large language models are making models of the world. I would say the model of the world is the part that I think have been missing a lot from a lot of the theories.
Not 5 minutes. 5 minutes? Are we at a 10? I do want to mention that last night Lenore got an email inviting her into the American Academy of Arts and Sciences. Can you hear me, or should I put on the, okay, good, let me try this. Let me start by saying a little something about myself and how we got into this. When I was a kid, I was a very dumb kid. I mean, the people here, you were all smart, but I was dumb. And my teacher in the 2nd grade told my mother, he may be able to get through high school, but he'll never be able to get to college, which upset her very much. It didn't upset me so much as I really wanted to be smarter. And I asked my father, what can I do to be smarter? And what he told me, like, how do you remember stuff? You just do. Well, that didn't help. And I kept on bothering him until at some point he had an idea. He said, if you understood what's going on in your head, you could be smart. And I was in the 2nd grade, and I remember very clearly thinking, that is the most wonderful idea I have ever heard. Just have to understand what's in my head. That was in the 2nd grade. In the 4th grade, I can remember walking around in our garden trying to figure out what's going on in the head. But it just seemed to me like there was a homunculus in my head looking out through my eyes, and that to understand what's going on, I'd have to understand the brain of the homunculus. And that was clearly a losing proposition. So that's fourth grade. Maybe I'll keep on a little bit longer. That was fourth grade. I did actually manage to get to MIT. So, but it's hard because I remember I had a very, very hard time in my freshman year. The other students, especially those who had gone to the Bronx School of Science, had it easy. For me, it was very hard, and I was afraid I would flunk out, but I managed to stay in. And I managed to stay in because at one point, a friend of mine came in and saw me with my physics book open, memorizing the formulas. You know, after all, the physics book derives these formulas, and then it puts them in the big box, and it was clear that what's in the box is the important stuff. So I was memorizing, and this friend of mine came and told me, you don't memorize. You don't memorize. What you just derive from F equals ma. Well, nobody had ever told me that, and it hadn't occurred to me. I was essentially being a scribe, and so that made all the difference. I went from getting a D in my freshman year in physics, after spending all my time just on physics, a D, and then that became a B, and then it became an A, all based on the fact that I finally understood that instead of memorizing, you derive. Well, that was amazing. I'm going to keep on with this. So that was great. When I was a sophomore, I took a course with Richard Schoenwald on Freud, and there's the standard edition of Freud is 21 volumes, and we went through the papers that Freud had written. So that was an attempt to be able to understand what's going on in the brain. And then when I was a junior, this Richard Schoenwald stopped me in the hall and said, a wonderful person has come to MIT, a neurophysicist, a neurophysiologist named Warren S. McCulloch, and you should go and introduce yourself to him. And so I did. I went in, I introduced myself, I said, I want to. Well, I did, before going in, I read some of his papers, and they were wonderful papers, wonderful. For example, Freud had written a paper called The Future of an Illusion, and McCulloch had written a paper called The Past of a Delusion. And he was just a wonderful writer. And so after having read this and found that he did some mathematics and it looked very reasonable, I went in and I said, I want to work for you. I want to be in your lab. So that was as a junior. And he pointed to the books in the Encyclopedia of Neuroscience that he had. And he said, well, read these books and then come back. I wasn't about to read those books, but I did manage, having read his stuff, I did manage to prove a nice theorem. And with that, he took me in. That was Warren S. McCulloch, Dr. Warren S. McCulloch. He is the person who, together with Pitts, defined the first formal neuron. The formal neuron as we know it. And they used, with this formal neuron, they proved that it's possible to use this neuron to produce a Turing machine. You can build a Turing machine out of these neurons. Except for one very funny thing. They needed to have not just excitation, but they needed inhibition. The neurons had to have inhibition, and the neuroscientist said, we've never seen it. Can't be. But, you know, it has to be, and in fact, that was one of the predictions, which turned out to be true. Probably end with this. Finally, McCulloch was absolutely fantastic. Fantastic. Anything I wanted to do, he supported. He helped me to go with anything I wanted to do. Yes. Until about 3 months after I started working with him, I came in and I told him, I want to work on consciousness. That's what I really want. And it's the only time in my life that he ever said, you will not work on consciousness. I remember his finger, I remember his vehemence. I had not, for this very positive person to suddenly, so vehemently say, I can't, that was weird. And then Walter Pitts, who together with McCulloch did this work, using the neurons to build the Turing machine, it was Walter Pitts came over and told me something that I already perfectly well knew. He didn't have to tell me, you know, there's this much skull between your brain and the outside, and there's no way we can do experiments and no way we can find out what's going on. I didn't have enough sense to tell him, you know, I don't want to build the wiring diagram of the brain. I wanted something that the fourth grader would understand. I didn't want the wiring diagram. I mean, I would be happy with it. I'd spent time trying to find out what was going on. But what I wanted was something like the CTM, something that from a high level would explain what's going on. And I am really so happy with the CTM because I feel I could now tell the fourth grader what he wanted.